Forward-swept wings destroy themselves. At high speed, the tip twists upward, increasing lift, which increases the twist. A feedback loop with no exit except structural failure. Every aerospace engineer in the 1940s called this configuration suicide. The Soviets built it anyway. What they discovered is that the same physics tearing a wing apart also produces something no swept-back aircraft can replicate. Full aileron control at angles where every other jet goes completely dead. To understand how a wing designed to kill itself became the most maneuverable configuration physics allows, you need to see what happens when a jet nearly stops. Here's what makes the forward-swept wing so dangerous. It's not that the wing breaks, it's that the wing breaks itself. And the faster you fly, the faster it does it. On a swept-back fighter, on airloads push the wingtip down and back. The angle of attack at the tip decreases. Less lift, less load. The system self-corrects. Forward sweep reverses that. When airloads hit a forward-swept wing, the tip twists upward. Higher angle of attack, more lift, more twist, more angle, more lift. Engineers call this aeroelastic divergence, a feedback cycle where the wing's own aerodynamic performance drives its destruction. Left unchecked, the wing twists past its structural limit, or the airframe enters resonance and shakes itself apart. Either way, the aircraft is gone. This wasn't theoretical. In 1944, the Junkers Ju-287 became the first jet-powered aircraft ever built with forward-swept wings. German engineers knew the divergence problem existed when they drew the design. They accepted it anyway. The war demanded results fast, and the Ju-287's low-speed handling was exceptional. At moderate speeds, it flew well. Above a calculated threshold, the wing geometry took over. Test pilots learned exactly where that line was and stayed below it. Not because the problem was solved, because it wasn't. Forward sweep was quietly abandoned. It disappeared from serious aviation for nearly a full generation. For the next 4 decades, aviation treated forward sweep as a closed question, too unstable at high speed. And the deeper problem, the one that made engineers give up, was that there was no fix within the physics of the configuration. The instability wasn't a design flaw, it was a property of the geometry. Sweep the wing forward, and divergence comes with it. No version of forward sweep was stable at high speed. Not with aluminum, not with steel. Then, in 1984, de Grumman flew the X-29. The X-29 was an American research aircraft funded by DARPA and NASA, built specifically to prove that forward-swept wings could be controlled in the modern era. It worked. But the numbers behind that statement are what matter. The X-29's fly-by-wire computer issued 40 corrections per second to prevent aeroelastic divergence from taking hold. Remove the computer, and the pilot had approximately 0.1 seconds before the feedback loop made recovery impossible. Not 0.1 seconds to react. 0.1 seconds before the window closed entirely. The X-29 didn't solve divergence. It outran it, using computers fast enough to interrupt the feedback loop before it compounded. The wing still wanted to tear itself apart at high speed. The fly-by-wire system simply won that argument 40 times every second. Consistently faster than physics could respond. That's exactly what the Soviets were watching. The Su-47 Berkut program launched in the late 1980s as the Soviet answer to the next generation of Western fighters. Forward-swept wings were central to the design from the beginning, not despite the divergence problem, but with full knowledge of it. Soviet engineers weren't dismissing 4 decades of aerospace history. They were betting that a structural solution existed, one that didn't require a computer correcting the wing 40 times per second just to keep the airframe intact. If the material itself could resist the twist, the feedback loop never started. The apparent impossibility is this: you cannot separate what makes the forward-swept wing destructive from what makes it effective. The same tip-twist feedback that drives structural failure at high speed is directly linked to the root stall behavior that gives the wing unmatched authority at low speed. Fix the destruction, and you risk erasing the advantage. They're not two separate properties. They're the same geometry observed at two different speeds. Building a wing that survives its own aerodynamics created something the engineers hadn't fully designed for: a jet that could physically do things the pilot's nervous system was too slow to command. The solution wasn't making the wing stronger. Stronger would have added weight and still failed. Aeroelastic divergence doesn't respond to brute force. A thicker aluminum spar resists the initial twist, but as speed increases and air loads compound, it eventually bends anyway. The feedback loop doesn't care how heavy the structure is. It exploits the geometry. The only path forward was to change how the wing responded to the load, not resist it, but answer it differently. The breakthrough came from understanding what divergence actually requires to function. The feedback loop depends on one specific property. When the wing bends under load, it also twists. In a conventional aluminum wing, bending and twisting are mechanically coupled. The material's elastic properties are identical in every direction. Engineers call this isotropic behavior. Apply load from any angle, and the material responds the same way. That's why aluminum wings bend and twist together, always. You can't separate those two responses without changing what the material fundamentally is. For 4 decades, that was the unsolvable wall. No alloy, no thickness, no geometry modification changed how aluminum's elasticity coupled bending to twisting. Carbon fiber composites are not isotropic. Their stiffness depends entirely on the direction you're measuring. Along the fiber, the material is extremely rigid. Across it, far more flexible. That anisotropic behavior, different mechanical response in different directions, means the engineer decides, during layup, exactly how the structure deforms under load. Not by shaping the material after the fact, by specifying the fiber angle before the panels are ever cured. This is aeroelastic tailoring. On the Su-47, carbon fiber skin panels were laid at approximately 15 degrees off-axis relative to the wing's primary load direction. When air pressure bent the wing upward, the off-axis fibers generated a compensating response, a slight twist in the opposite direction from divergence. Bending and twisting still coupled, but now they coupled the right way. Instead of increasing the angle of attack under load, the wing geometry slightly decreased it. The feedback loop had no foothold. Physics was operating normally. The material was simply answering in a different direction. The Su-47's airframe was approximately 90% composite by structural component, not just skin panels, but primary load-bearing structures throughout. That figure reflected both the divergent solution and the manufacturing philosophy the solution required. You cannot aeroelastically tailor an aluminum wing. The solution to forward sweep instability was inseparable from building the entire aircraft around composite construction. Composites weren't a performance upgrade. They were the prerequisite. What made this solution elegant was its passivity. The tailoring required no sensors, no software, no real-time correction. Just a structural property that reliably worked at every speed, every altitude, every temperature, without any active input from the aircraft's systems. This wasn't exclusively a Soviet discovery. Boeing's 787 Dreamliner uses aeroelastic tailoring in its wing design. The dramatic flex visible under high-load conditions is intentional, engineered through fiber orientation to reduce structural fatigue and improve ride quality. The principle is identical to what the Su-47's engineers solved. The application is commercial aviation carrying 300 passengers across oceans. The same physics that nearly made forward-swept wings impossible ended up making composite wings better across the entire industry. What the Su-47's engineers achieved was specific: a forward-swept wing that resisted divergence not through active correction, not 40 fly-by-wire interventions per second, but through the passive structural behavior of the material itself. Remove the computer, and the wing still didn't want to tear apart. The solution was embedded in the airframe at the molecular level. The X-29 proved forward sweep could be managed. The Su-47 proved the management could disappear. The structural problem was solved. What the wing actually unlocked had nothing to do with how fast the jet could go, and everything to do with what happens when it almost stops. On a swept-back fighter, the wing stalls tip first. As the pilot pulls back and the angle of attack increases, Airflow separation begins at the outermost section of the wing before anywhere else. That's where the ailerons are, the control surfaces that govern roll. Lose flow attachment at the tip, and you lose roll authority. The pilot can no longer control which way the aircraft banks. At extreme pitch angles, swept-back jets go aerodynamically deaf. The nose points wherever momentum carries it, but the pilot is no longer directing. The aircraft is falling with attitude, not flying with it. Forward sweep inverts that sequence entirely. The stall begins at the root, the inboard section, closest to the fuselage, and progresses outward only as the angle of attack continues to increase. The wingtips, where the ailerons sit, you remain in clean attached airflow long after the root has separated. At 45 degrees angle of attack, at 60 degrees beyond, the ailerons are still working. The pilot still has a roll control. The jet can point its nose at angles that would leave any swept-back aircraft fully uncontrollable and still respond to inputs. That is what fly backwards actually means. Not sustained reverse flight, the Su-47 wasn't designed to cruise in reverse. What it means is this: the jet could pitch its nose through extreme angles, past vertical, continuing through 120, 180, and all the way to 360 degrees, while maintaining enough control authority to complete the maneuver without departing controlled flight. The Kulbit. A complete forward loop at near zero airspeed, the jet momentarily traveling backward relative to its original flight vector at the loop's apex. On a swept-back fighter, the ailerons die before the nose completes the rotation. The maneuver terminates in an uncontrolled departure. On the Su-47, the ailerons stayed alive through the full arc. The pilot completed it cleanly and flew out the other side. The tactical implication is specific and direct. In a close-range engagement, a pilot who can point weapons at a target that has already flown past, while that target's aircraft is still turning to acquire a firing solution, wins before the other pilot even recognizes that the geometry has shifted. The Su-47 never entered mass production, and the reason has nothing to do with whether the wing worked. By the time the Berkut was flying demonstrator missions in the late 1990s, the definition of a frontline fighter had shifted fundamentally. Fifth-generation programs demanded radar cross-section reduction as a primary design requirement. Not secondary, not a late-stage consideration, but a hard constraint shaping every surface from the first design review. Stealth platform geometry requires specific features: aligned leading and trailing edges, carefully controlled surface angles, no sharp discontinuities that scatter or return radar energy. Forward-swept wings produce a radar cross-section estimated between 3 and 5 square meters on the Su-47, roughly 100 times larger than the F-22's. The same geometry that gave the wing its aerodynamic character made it radar visible at a fundamental physics level. No design modification fixed both simultaneously, so the Su-47's wing was either aerodynamically exceptional or stealthy. Not both. The program ended as a proof of concept, but what the engineers proved didn't disappear. Aeroelastic tailoring in carbon fiber composites, the structural solution the Su-47 required just to survive its own flight, transferred directly into the Su-57 program. The forward-swept wing was gone. The composite engineering methodology that made it survivable became foundational to the next generation of Russian combat aircraft. The Su-47 never flew in combat. Its materials, science flew in everything that came after it. The suicide wing worked exactly as designed. The world it was built for had changed. If you want to understand what a fifth-generation stealth fighter trades away for radar invisibility and why that trade-off costs more than most people realize, that video is already made.